the last session, we were talking about the waves and things. This one, we're going to look at the electromagnetic spectrum, okay? We're going to be talking about how, or basically we're talking about electromagnetism. Now, just let's analyze the word itself, right? Let's put in here electro and electromagnetic, okay, spectrum. Okay, electro comes from electrical, magnetic obviously, and the spectrum is a range, okay? A vast spectrum of opportunities, vast range of opportunities that you have. Electrical and magnetic range, okay? It's fundamentally, we're going to be doing it in terms of wavelengths, okay? So let's just look, and in your books it's there. We've got wavelengths in meters, we've got radio over here. This is long. You can have it of, in meters, 10 to the 8 down to 1 meter. Microwaves, okay? Microwaves, 10 to the minus 2. Okay, these are all in your books. Infrared, that's just below red, and here is the visible. Okay, the visible. Now there's a way of remembering this. Roy G Biv. Roy G Biv. From long to short. Okay, the wavelength. This is all wavelengths here. Okay, Roy G Biv tells you the colors red, orange, yellow, green, blue, indigo, violet. That's the one just between. Then we go on to the UV, ultraviolet. We all know about that from the sun. And we move up through basically here, X-rays, up to gamma cosmic rays that are coming at us from the things happening out there in the universe, right? So this is the visible part. So you can see there's only a small part that we can see, all right? We're not sure if people can see into the ultraviolet, or rather if animals or whatever can see in the ultraviolet, or in spectrums less than us. We don't even know if animals see in color. Most people think, I think those of us who have animals tend to think they do. We hope they do. But anyway, so this is the electromagnetic spectrum, all right, that we are going to deal with over here. Now, there's an interesting thing. Let's just look at light. Okay, let us look at light waves, okay, itself. Now, all of us have heard of photoelectric cells, right? In the whole issue of clean power, many places, especially in Germany, they've put up huge banks of what they call photovoltaic cells. It's just taking and creating electricity from the sunlight that falls, right? So areas in, for example, the Karoo, the Namib, the Sahara, you could have banks of these things because it's sun most of the time. And generally what they do is they create electricity from the sunlight. Now, let's just have a look. How does this happen? Well, we've got a metal over here. Okay, so the sun is shining on this metal, right? And what happens if, not all metals do this, okay, but as the sun shines on it, as the rays of the sunlight hit it, we notice that if we have an ammeter which measures the current flowing, the electrons flowing around, we'll get to this, we find that we see a current, I. It's all coming up in later sections. What is happening here is that in essence there are electrons flowing, right? Now, what do we know? We know that inside a metal the electrons are sitting in a delocalized cloud, aren't they, around the nucleus. And as we say, an electron comes in, another one pops out at that end. So what is happening here is that the sunlight, because if we all of a sudden stop this, the current stops. So these electrons are moving. Okay? They are creating a current. So light waves must be coming along and knocking electrons out. All right? But we know that light behaves as a wave as well. Now we're saying it must be behaving as a particle because it's knocking something out of its position. And when we've got something that is moving, okay, moving means it is kinetic, right? The word kinetic means movement. Kinetic means movement. So we are getting kinetic energy, we are moving it. So what actually happens here is this. It is postulated that, remember, we start off with velocity of a wave is equal to frequency times the wavelength. Now, all electromagnetic waves travel at 3 times 10 to the 8 meters per second. What is that magic number? That is called the speed of light. 3 times 10 to the 8 meters per second. It is a constant. It does not change in the experiments that we're going to do here. Right? So we've got the constant, the speed of light is taken as 3 times 10 to the 8 meters per second. So that's the same concept really. Remember we did velocity of sound in air is taken as 340. It doesn't matter where you are, it travels at that speed. Okay? It actually in reality does. It depends on pressures and temperatures, but let's just leave it. Light is the same concept, it's a constant. What is happening? The light is coming in at that. So now we change it to C equals frequency times lambda. Right? So what happens here is that in essence, okay, this light must have energy to be able to knock electrons out of their orbitals, because we're taking them and we're saying you're out your orbital, off you go, and you're now part of a flow of electrons, you're a current. So what happens is as we come in, the electromagnetic waves come in, C is equal to frequency times lambda. What actually happens is we say this is our metal here. Okay. What we do is we take, okay, here's the light wave coming in, right? What we do is we parcel up those waves, say, into a package. We call that a package, okay? So all of it is in little packages. So the light is a wave, but it's delivered in packages which we give a name. We call them quanta. Okay? That's plural. So the singular is quantum. Okay? You've heard of the term quantum mechanics, quantum physics, all right? The stuff that they're dealing with at university and so forth. Quantum mechanics, quantum physics. These things here are dealing with packages, this kind of energy. So now we say, well, how much energy is in here? How much energy is inside each package per package? Okay? The energy turns out to be HF, right? F is frequency. Okay? H turns out to be something called Planck constant. Okay? It's a number which is a constant. Okay? So this is called the photoelectric effect. You might have seen those little cars. You can buy them at the hobby shops. They're a little car with a solar panel on it, and the moment the sun gets on, and the car will go. The moment it falls into the shade, the car stops. Okay? So the photoelectric effect is responsible for the photon generates electricity. Photoelectric effect. That's what's causing the flow of electricity. That's what's powering the little motor in the car, in essence, right? So this photoelectric effect is quite important for us, okay? Because what we do is we can actually use it to our own benefit, obviously, because now it means that we can power things using the energy from the sun. Just let's have a look here. E is equal to H times frequency. But also remember C is equal to lambda times frequency. Therefore, okay, we could say that F is equal to C divided by lambda, just changing it, which means this formula can also be H times C over lambda. You are given this formula in the schedules anyway, okay? But just so you know, it's HC over lambda. That's the photoelectric effect. So what is a photon? Is an energy package. It comes in and it knocks an electron off and causes a flow of current. That, in essence, is the photoelectric effect, okay? What I'm going to do is I'm actually going to cut this one as a short one, okay? Because the next chapter is going to be a chapter on which we're going to be talking about magnetism and electricity. Okay, I don't want to start it because that's going to be quite a chapter. So I don't want to do bits and pieces. But just as a general talk of it, we're going to be talking about magnetism now, and we're going to talk about electricity. Okay, what is a magnet? Well, we know what a magnet is. A magnet has got a north and a south pole, and here's some of them, for example. Right here they are. I'll just put them on this piece here. There you are. He rolled off because he's got the weird shape. Okay, and they attract each other and they repel each other. You must have taken magnets, a north pole and a north pole, and pushed them together. They tend to repel each other. South and south repel, right? So like poles, okay, repel. Okay, unlike poles, what happens? Why are these things stuck together? We're going to go through this, but just an intro. They are stuck together because of a magnetic force. There has to be a force because what's holding this up from falling? There's a force of attraction there. This is pulling that up, okay? So, therefore, in magnetism, we've got a force acting, okay? A force of attraction, equally a force of repulsion, okay? The other part of this is over here is that we're going to be looking at these forces. We're going to be talking about how we push together, how much the force is going to be. Then we're also going to look at charges. We're going to look at electrostatics, where we've got things that are positively and negatively charged, okay? But I'm going to cut this one short now because I don't want to get really started and get into it, and I'll see you in the next one, which is going to be on magnetism and electricity. By the way, the photoelectric effect gets dealt with again in grade 12. It's also, obviously, it's quite a big thing if you're going into the electronics industry or electrical engineering for that matter. And currently it's flavor of the month because why? Because everything we're looking at is green power, sustainability, sustainable energy. You can imagine, as I said, the Sahara Desert. Imagine the amount of electricity that could be generated from panels there. Your problem? Dust, dirt, right? They've got to be cleaned off and it's a huge maintenance thing. So yeah, there's pros and cons of everything. We'll see you in the next session. Thanks for watching.